if I could have your attention for a few minutes. I want to talk a little bit about using SolidWorks to do a thermal analysis. Okay? So the idea here is that thermal analyses can be very much analogous to structural analysis. And so I wanted to talk a little bit about how those are similar to each other. And I wanted to give you a really basic introduction to doing it. And mostly the reason for that is so that if you ever are in a situation where that might be useful to you, you have some idea of how it's done. Okay? So I want to talk for just a few minutes. This is going to be a short one. This will be the last content that we're going to go over for the semester. So this will be associated with assignment 10, which will be the final assignment for you for the semester. Okay? So we're going to do that today. I'll talk for just a few minutes and then tell you about what assignment 10 is about, and then you should have plenty of time to continue to work on assignments. By the way, I've worked quite a bit the last couple days on grading some assignments, so you should see those hopefully showing up. Pretty much if you've turned in assignments up through, I think I've got all of them done through 4, and then a few through 5 and 6. So if you have any questions about those, please let me know, and I'll be happy to discuss any of that with you. Okay? All right, so thermal analysis. The thermal analysis is the calculations of temperatures at particular locations in the body. And what we're going to see here in a minute is for thermal analysis, the temperature at the nodes is going to be completely analogous to the displacements at the nodes that we do with structural analysis. And if we can calculate the temperatures at locations in the body, then we can determine information about the magnitude and direction of heat flow in the body. And from that, then we can get an idea of the thermal performance of the structure. So, can you think of examples of places where I might be interested in a thermal analysis of something? Okay, heat sink is an obvious one. I don't know how many of you have torn open a desktop computer and looked at it, but you know, there's typically some big heat sinks stuck to the various components in there, your graphics card and such. If you wanted to try to optimize that, having an analysis of the thermal performance of it would be useful to us. What else?
Is there anything you design that's going to be in a hot, you know, have a lot of thermal energy, like I guess like furnace or something?
Okay.
Design parts for that.
Sure. Yeah, if you're going to design a part that's going to be in a high temperature environment, you might want to know a little bit about how it conducts heat. Okay. I told you I used to work for a company that made conveyors, and one of the types of conveyors we had fed furnaces. And it would be filled up with metal scrap, and it would roll up to the furnace, and actually the end of it would stick into the furnace, and then it would convey the material into the furnace. And clearly that end piece that's stuck in the furnace is getting a lot of heat. And how does that transmit back down the conveyor? And do we need to be concerned about, you know, where's the motor located and how much heat is it actually seeing? Where various springs or other components, you know, what is the likelihood of them exceeding their operational temperatures? Clearly that would be something important to know. Okay, so lots and lots of applications. Electronics are really obvious. I was using my Surface yesterday, and I had plugged it in for a while, and it was being charged, and I set it on my lap, and it was, you know, noticeably hot sitting there on my lap. So those are really obvious examples. Engines and other manufacturing applications would other places would be interested in this too. Okay, so for example, if we compare heat transfer to structural analysis that we've been doing, there are lots of analogies. You think of convection and radiation as surface loads. Internal heat generation would be a body load. So an internal heat generation, charging a battery would be internal heat that's being generated. That would be similar to structural application to gravity effects on a structure. And then we can do stuff like prescribed temperatures, similar to saying that we're going to deflect an inch at the end of this beam. You can say, well, it's going to have a temperature change of some amount at the end of the structure. So I put together a table that kind of shows the things that are related to each other, structural analysis versus thermal analysis. So in structural analysis, displacement is equivalent to the temperatures in a thermal analysis. And I also put some units in here, and some of you, incidentally, on your assignments are not including units. And I'm afraid that in some cases you might have the right answer, you've just put it in inches, and I did it in meters or millimeters. So I've been marking those on yours. Make sure you're not doing that and inadvertently getting stuff marked off just because I didn't do it in the same temperature or same units that you did. Strain would be analogous to a temperature gradient. Temperature gradients in structures are going to be of particular interest to us. A lot of times a temperature gradient then can result in structural problems. When I was working in industry, we had machines that had portions of them at very high temperatures, and the temperature gradient would cause internal stresses. So these are analogies in the analysis, but a lot of these are also interrelated into actual performance of the piece. Thermal. When we know the temperatures of something, we can also then predict stresses and strain. Stress is similar to heat flux. Loads in a structural analysis are going to be analogous to heat sources, and then a prescribed displacement that we talked about is analogous to a prescribed temperature. Okay. So we can think of our thermal analysis. I'm not an expert on thermal analysis. I'm not an expert on thermodynamics. I'm not an expert on fluids. So when I think of a thermal analysis, a lot of times I relate it back to what is it like in a structural application. Okay? So having a charging battery that has a heat source that is heating up is similar to a load, a force on the structure that's obviously going to affect it. So that's the way mentally I do it. If you're a thermal type person and you're comfortable with those concepts, then maybe you don't do that translation. Clearly, as you get better at this, you don't need to think of it in that way. But I like this table because it helps me think about how, what kind of things do I need to put on my model. So for example, I'm really comfortable with, I create my geometry, and this is going to be exactly the same for both types of analysis. I create my geometry. What's the next thing I do? Well, I got to put some constraints on it. Okay? So in the case here, constraints would be essentially places where loads are, right? And so depending on what my constraints are, they're going to be, I'm going to need some heat sources for my thermal analysis, or possibly, depending, prescribed displacements could also be a constraint. For example, my prescribed displacement could be 0. If I've got a support where it doesn't displace, then it's 0. So I know the temperature at that point. That's my constraint in my thermal analysis. Next, I put on some, I'm going to put some forces on it in my structural application. For my analogy here for thermal, then I need to say, where are the heat sources? Are they internal? Are they external? Is it radiation that's coming onto the surface from an external source, or is it heat generated inside like an engine is generating the heat? And so then I put the forces on there. So how does this all relate back to using SolidWorks and such? Well, I think I told you at the very beginning of this semester that our KD equals F equation can be reformulated for a lot of different applications. can use that same equation or that same pattern, that same analogous equation in fluid mechanics, for example, which we haven't talked about at all here. But in thermal analysis, we get something that looks very similar. We get slight changes in our what our equation is. We have something that's K, which is related to the conductivity of the body. We now have temperatures instead of displacements, and we have the thermal loads instead of forces. But the math there is exactly the same, right? So what that means then is I can write a computer program that solves that equation, and if I just put in temperatures instead of displacements, and if I put in thermal loads instead of structural forces, then I can use the same solution algorithms to solve a completely different type of problem. Okay? So that's all this is here. Is we're using the mathematical framework that's already been generated to solve a different type of problem, a thermal problem instead of a structural problem. Okay? Does that make sense? Seem reasonable? Okay. The one little hiccup of this is that for thermal analysis, our conductivity is a function of the temperature at the nodes. So as the temperature changes, the conductivity changes. And so that means that this is actually a nonlinear type of problem. Okay, so there's that little complication here. And so what typically does, SolidWorks, I said, is a linear type software. And so what typically is, I don't know the details of what SolidWorks does, but what typically is done is it does a type of iterative thing where it predicts all the temperatures and it goes back and it adjusts the K value for those temperatures and runs it again and just iterates that until the error is small in the changes in temperatures. Okay? All right, so here's a general body subject to the thermal loads, different types of things that might be going on that we could solve using SolidWorks. We have prescribed rates of heat flow across the boundary. We can have internally generated heat. We can have insulation, so there's no heat. Prescribed temperatures, radiation, and convection. All of those types of things can be accommodated using the various types of loads and constraints that we can set up using SolidWorks. Okay, so there's a really brief introduction to what is it that we can do with a thermal load. The textbook that I recommended you get does not have a thermal analysis in it. And so what I did is I put a PDF under assignment 10 that has kind of a step-by-step, how do you do a thermal analysis? And to make this, I guess partly because of my own not as familiar with thermal analyses, I felt like maybe you guys could probably use a little bit of extra help too. And so the way I formatted assignment 10 is that you pretty much go through the tutorial. Okay? And it shows you exactly, it tells you exactly how to set up a thermal analysis. So this one will be easy. This one will be a cookbook type assignment. Just go through the tutorial and do the analysis, and you can even check your answers because it will tell you what you should be getting, and you can make sure that you're getting what you should be. To make life even easier, I even gave you the part files that are going to be analyzed. So when you look at assignment 10, there are 2 parts attached. Those part files are the part files that are going to be used in the tutorial. And you can follow through, and it'll say, put prescribed temperatures on this particular surface, or put a heat source on this surface, and then it'll go step by step through that for you. Okay? So, if you need to knock out an assignment really quickly and you don't, it's late and you're tired and you don't want to have to think too much, This might be a good one to try to knock out, because it's pretty much a cookbook type of thing. You don't have to go back through 211 and find out where the equations are to do your hand calculation or any of that kind of stuff. Okay? Any questions about any of that? Okay, that's the last assignment.